Anyway, so we learned about the Lorentz force law. Force is a vector. It's equal to the charge times the electrical field plus charge times the velocity cross product with the magnetic field. And cross product just means you're going to take the perpendicular component between the velocity vector and the magnetic field. So if you have a magnetic field, and let me grab my other ones. Probably dry it out. Then get it right. Okay. And let's say we have a velocity. And this will be your magnetic field. I believe, I'm not 100% sure. Let me double check, actually. Because with torque is R, your displacement from the pivot point, cross product with force. So let me see. Force, our torque equation. I don't think it actually matters. I think it works out when you look up cross product of vectors. I don't think it actually, actually doesn't matter. Because it's the angle between A and B. So it's some angle here, theta. So this would be the magnitude of the velocity times the magnitude of the magnetic field times sine of theta is what this is equivalent to. These absolute value marks mean, so we have some vector. So that would be equal to the square root of Vx squared plus Vy squared. The two components. But this it turns into a scalar. Basically, it's just a number. My point of drawing like this is that we take the perpendicular component, this one, and it would be just this times that. Likewise, you could have instead done, this is the point I was trying to make, we could have also done the perpendicular right here of the magnetic field and multiplied it with this, and it works out the same thing. So it doesn't matter which one you choose to make perpendicular. It's just you just use the angle between them. Thus, the reason why this works when you have a torque is the angle between them is right here. So if this is force and this distance right here is r, then the angle between them would just be Rf sine theta is equal to the torque. So let's design a velocity selector. By the way, this website right here is called Hyperphysics. You can Google it. It looks like this. This is a very, very useful website. I personally use it for a lot of things. It's very high level sometimes, but at the same time, it explains things very, very well. So where is Ren's force law? So what this equation tells us, this portion right here tells us a moving charge in a magnetic field experiences a force proportional to the charge, velocity, and strength of magnetic field. It also tells us that it's a cross product, so only the perpendicular component matters. Because it's a cross product, what that means is if we have a magnetic field like this, we have a north and a south. We draw the lines from the north like this. What this means is if we have a positive charge moving in this direction, or a positive charge moving in this direction, the force due to the magnetic field is zero. Whereas a force moving in this direction would experience the full force. Whereas a force moving in this direction, only the one that's perpendicular to the magnetic field, the component actually contributes. So let's make a ray gun, or a particle gun. One of the very easy particles to generate is called an alpha particle. Do you know what alpha particle is? It is a helium's nucleus. In radioactive decay, specifically alpha decay, a helium's nucleus is ejected out of the nucleus of larger atoms. It is 2 protons and 2 neutrons. So it would have a charge equal to plus 2e. And E is equal to 1.602 something 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 times 10 to the negative 19. So 0.602, 176, 634 times 2. So it has a charge equal to plus 3.204. Its mass would be 6.645 times 10 to the negative 27 kilograms. And how fast do you want this gun to shoot at?
don't know what the number is.
Let's break the sound barrier. Sound barrier is 340. Let's go with 1,000 meters per second. Crazy fast. So we're going to build a selector that is going to fire. So we have some source. And technically, it's you can vary this to actually determine the speed at which particles leave. You can keep changing these values until you start seeing particles come through. And by using the values you set, you can know exactly what the speed of the particles being ejected are. So we have some source that are emitting alpha particles. It's Greek letter alpha. And over here, we have a tiny little hole. So only ones that have gone straight through will actually leave the gun. So we need to rule out any ones that are moving too slow and too fast. So we can ignore gravity too. Let's ignore gravity and assume this is in outer space. It doesn't make too much difference. Let's first get the ones moving too slow. So I'm going to add some parallel plates. Make this one negative and make this one positive. Thus, between these two plates, it is going to experience a force equal to Q times E. So so it's going to be pulled downward. This force is going to want to pull it downward. And we need a counter force that will push it upward. And we can do that by adding a magnet, north, and south. And the strength of this field is going to be FB is equal to QVB. We can ignore the fact that it's a cross product because it's going to be perpendicular to it no matter what. So when will these objects actually make it to the hole? So this one is going to want to pull it in the direction. So if it's a positive charge, so it's going to want to be attracted downward. So looking at it, drawing our axis. This is the vertical axis, this is the horizontal, and this is the forward, backward one. So this electrical force is going to be directed downward. And what direction is going to be the magnetic force? So the magnetic field is going to be pointed in this direction. The velocity is pointed in that direction. So if I point my thumb in the direction of the magnetic field, or the velocity, and my fingers in the direction of the magnetic field, my palm points in the direction of the force. So it'll be upward toward these plates. So the magnetic field is upward. In order for it to go straight, we need zero force, right? We need these two forces to cancel each other out. So only particles that have zero force will actually make it through. And if we make these extremely strong, then only exactly those that have the right velocity will make it through. So we want and combining it together. We want the force to be equal to 0. Since these are in opposite directions, this one will be negative and this one will be positive. We want these two components to be equal. Thus, we want the field strength. We want the electrical force to be equal to the magnetic force. We have a Q on both sides. We can eliminate that. And because they are perpendicular already, we can get rid of the cross product. And solving for velocity, velocity is thus equal to and I need to really remove the vector notation. The electrical field strength divided by the magnetic field strength. So we want these values to be the same. By the way, going up here, another way of writing this is factoring out the Q like this. I have seen it written this way. You can factor out that Q because it's a scalar. So we have the values. Let's use another sheet of paper. So we have an alpha particle. Its charge is plus 3.204 times 10 to the negative 19 coulombs. And its mass is 6.645 times 10 to the negative 27 kilograms. If we needed to concern ourselves with gravity, we'd have to use the mass. Let's do the calculation without it, and let's assume that we have a magnet, a permanent magnet. I think you really can't get a permanent magnet this strong, but let's say we have a magnetic field of 0.5 Teslas. What this means is, and if we want the velocity to be 1,000 meters per second, then we can solve for the electrical field. We know that the velocity is equal to E over B. Solving for the electrical field, we see that the electrical field would thus be equal to the velocity. And again, I need to remove the vector notations because this is assuming we converted it to scalars. And thus, we plug in 1,000 meters per second, 0.5 Tesla, and we get 500 coulombs, which is a crazy newtons per coulomb. Actually, that's not that bad. That's actually a weak electrical field. So in order to ensure that only particles moving at 1,000 meters per second with a half a Tesla, and no, it doesn't depend on charge because it cancels each other out. It only depends on the field strength and the field strength of both the electrical and magnetic properties. If we were to change this up to include gravity, how would that change? So we'll have a force equal the electrical force equal to Q times E. We'd have a downward force for gravity, which would be equal to, I'm going to ignore I'm going to assume I'm on Earth and just use mg. And I'd have an upward force equal to qvb. And I want the total force to equal 0. So I'm going to go ahead and plug negatives into this. My total net force, I want it equal to 0. And it'll be equal to, starting with this one, QVB minus QE minus mg. So again, I'm going to assume that I'm fixing these values and I'm trying to solve for how much electrical force is needed, or electrical field is needed. So solving for E. Moving this over, I get QE is equal to QVB minus mg. Note, by adding gravity to this, it actually depends on charge now. Previously, when I ignored gravity, charge didn't matter. Now that I'm adding gravity, charge actually matters. So dividing by Q, I get VB minus mg divided by Q. So I still get the 1,000 meters per second times a half a Tesla, which is 500 newtons per coulomb. That's what I got last time. But now it'll be minus 6.645 times 10 to the negative 27 kilograms times 9.8 meters per second squared, divided by 3.204 times 10 to the negative 19 coulombs. And let's see what that gives us. Should be a crazy small number. So minus 2.0325 times 10 to the negative 7 newtons per coulomb. Kilograms times meters per second squared is a newton. And thus, this is still roughly equal to 500 newtons per coulomb. So even including gravity into this, it doesn't actually change too much. It would perhaps start... actually, no. The stronger the charge, it would not, and we're already at the limit. The only thing lower than alpha charge is just a single proton. We're just so we're at double the lowest possible number. All right. So you think you got force down? So let's actually generate some magnetic fields. This is a very, very important concept. A moving charge produces a magnetic field around it. So a moving charge produces a magnetic field around it. Let's suppose I have an infinitely long wire. So an infinitely long wire. You can approximate this by having a finitely long wire, but really that's a poor approximation. I mean, it's infinitely smaller than an infinite wire, but it's close enough. Mathematically, it has to be infinite, but even if you approximate it to like a few feet, it still works. Um, uh, just pull this up. Ampere's law. So the magnetic field of space around electrical current, so electrical current is moving charges, is proportional to the electrical current which serves as its source, just as the electrical field of space is proportional to the charge which serves its source. Ampere's law states for any closed loop, the sum of the length around that times the magnetic field and direction, blah, blah, blah. Advanced calculus. If you draw any random loop, the sum around that is proportional to the permeability times the electrical current and closing the loop. So basically what this all states is if you have some charges moving along a wire and you randomly draw some sort of closed loop around it, and you were to sum up an infinite number of spots around this loop, then the sum is going to equal some permeability, blah, blah, blah. For this class, we don't have to concern. We'll use perfect circles. Perfect circles is good enough for this class. But the correct law is way more generic because you can do any loop. So let's say that the current going in, and current is represented with an I, so electric current, i.e. moving charges, is going to the right. If you put your thumb pointing in the direction of the current and wrap your fingers around the wire, the way you wrap your fingers is going to be the direction of the magnetic field. So I'm going to go underneath, wrap around, and point it toward me. So it's going to come around and wrap like this. So this magnetic field here. Thus, this magnetic field for a circle of radius r will be equal to the permeability of free space times the current divided by 2 pi r. Two pi r is the circumference, it's the length of this rope, or this circle, right? So it's basically dividing by the length of whatever circle. So this right here is the permeability of free space. Also known as the magnetic constant. So this is the vacuum permeability. Not to be confused with permittivity. And mu naught is equal to 1.25637 times 10 to the negative 6 Henry per meter. A Henry per meter is equal to a Newton per square meter, or square ampere. And we'll stick with that. So, magnetic permeability. It used to be an exact number, we define it. But we now change the definition. So 1.2566 times 10 to the negative 6 newtons per ampere squared. This is electrical current measured in amps. And this would be radius from circle. From center of circle, radius of circle. Measured in meters. So, what's a good amps have you run through a wire? What's something you use maybe in an ag shop that runs a lot of current?
Use the load machine.
How much current does it run? So that's a crazy, stupid high amount of amps. In your household, if I remember correctly, 15 amps by law is for anything that continuously runs, with exceptions of your washing machine, your oven, and your dryer. They can run up to 20 amps continuously. No, some of them run like 600, but they require specialized circuitries to run. So, welding amps. Yeah, 300 amp stick. I forget how they achieve the 200 amps. I don't think they're drawing 200 amps from the wall. They might be. It's doing a crazy amount of stuff. It maybe does. But 300 amps is crazy strong. So your household is usually max. So a hairdryer doesn't meet the definition of continuously running. You only run it for 5 minutes, usually. So they're allowed to use the full 20 amps. But like a space heater can only max out at like 15 amps. This is because any wires aren't up to code. If run at 20 amps for a long time, might catch on fire if they're poor or haven't been replaced after a few decades, because it generates a lot of heat. But let's actually do 20 amps first. So your washing machine or oven, electric oven if you have one. And then we'll do it for 300. So, or current is 20 amps. And how close away do we want to measure the strength? Let's get right up on top of it. So let's assume that our radius away from it is 1 millimeter. That's like right touching it. Let's make it 2 millimeters. Or 1 millimeter. What do you think? 2. Okay. It's some thick wire. Again, it's the radius of it. So we have some wire. It has 2 millimeters away from it. Technically, we're not dealing with a vacuum. We're dealing with plastic. But plastic won't affect it too much. Technically, plastic, air, and vacuum are basically all the same thing. It's until we get to iron as a core that this changes, and this number only goes up. It'll only get stronger with iron. And we're running 20 amps of current through it. So that means the magnetic field strength at 2 millimeters away from the center of the wire would be equal to this. So that would be 1.2566 times 10 to the negative 6 newtons per ampere squared, times the current. The current is 20 amps. And 2 millimeters, so 2 times pi times 2 millimeters, or just divide by 1,000, 0.002. But you are right. We would get a value of 0.001998986 Teslas. So roughly equal to 0.002 Teslas. What would that be in Gauss? There's 10,000 Gauss in a Tesla. So I need to multiply this number by 10,000. So 20 Gauss, which is usually abbreviated as 20G or 20GS. I use capital G, but it does get confusing. And Earth magnetic field strength is 0.3 Gauss. So we are already using a crazy amount of amps. We're about 67 times the strength of Earth's magnetic field at a radius of 1 Earth radius. Don't get me wrong, Earth's magnetic field is very, very, very strong. It's just that we're very far away from the center. So if we instead did it for 300 amps, going in and changing that number, it would give us a magnetic field strength of approximately 0.03 Tesla. Multiplying that by 10,000 is 300 Gauss. And if we decreased that to, so this is for 2 millimeters, if we increase that to 1 millimeter, which I don't think you can run 300 amps through 1 millimeter radius wire, it would only change it to 0. It'd just double it. So let's do a problem. Let's say I have 2 wires. Going through this wire is I1. And going through this wire is I2. And they're at a distance R. So because there's a current going through this wire, it's going to create a magnetic. And putting my finger in the direction it's moving and curling it around, I curl it around like this. Thus, it would be around like that is my magnetic field strength, a radius of r. So I know that this field strength around the first wire is equal to I1 times 2 pi r. What would be the force on the second wire? So this is infinitely generated down all the way down this wire. So every point is going to pull on it. I'll go ahead and give you the solution. The force on the second wire, so this is wire 1, this is wire 2. I'll call this B1. So the force is going to be equal to the current going through this wire times some length times this field strength over here. We know that B is equal to this. So let's factor out per unit length. And we know B1 is equal to this. So the force per some unit length is going to be equal to, plugging this into this right here, I get this equation. So this a wire. By the way, if these currents are in the same direction, would it be an attractive force or repelling force? So what direction is the charges moving in? It'd be moving north. We assume current is positive charges, by the way. So by convention, current is positive charges. So it's moving in that direction. So that's our velocity vector, moving at some velocity. Current is moving downward, so my palm would be pointing inward. The force would be attractive. So we'd have a force per inch or something like that. We have so many newtons per meter.